find steady state error, there are two error constant methods. One is static error constant method, that is steady state we have seen. Now we will come to generalized error constant method. So let us take closed loop block diagram where you have forward path transfer function g, feedback path transfer function h, and I have input r of s and output c of s. And we had already defined what is error here. So this is after summing point we have error. We know how to get the error function. I am taking directly the error function. The error function E of s is r of s divided by 1 plus gh of s. I can slightly split into two terms because there are two terms in your steady state error function. In error function we have r of s and gh of s. I want to separate those two terms. So I can write E of s is equal to 1 by 1 plus gh of s into r of s. I will keep the r of s as it is, and this 1 by 1 plus gh of s I will write it as f of s is another function. So now f of s is 1 by 1 plus gh of s. Then how do you write the E of s now? E of s is equal to f of s into r of s. Here I want to use convolution theorem or convolution integration to find the error in time domain. So how can you write this E of s into f of s to r of s? When you apply the convolution integral, E of t is equal to integral minus infinity to plus infinity f of t into r of t minus t into dt. So in f of t is a capital T and r of t is small t minus capital T, and we have dt where t is a capital T. Now look at the integration, it is minus infinity to plus infinity as per the definition, but in control system we take always time from 0 to infinity, not from minus infinity to infinity. Therefore I can rewrite it as, so you have E of t is equal to integration 0 to infinity and f of t r of t minus t dt. So in this case we have input r of t minus t. So t is a small t minus t is a capital T. So let us expand this using your Taylor series. So when you expand using the Taylor series, your r of t minus t is equal to, we have r of t minus capital T r dot of t plus t square by 2 factorial r double dot of t and minus and so on. So this r of t minus 2 I want to substitute in the error function E of t. So what we will get? E of t is equal to, your integral 0 to infinity is already there, f of t is already there, and open the bracket and substitute that r of t minus t. So if you substitute that, the same thing you will get r of t minus t into r dot of t plus t square by 2 r double dot of t minus dot dot and so on, and after that we have dt. This is E of t function. Now this integration I want to push it to every individual term. So we can easily write integration to each individual term as E of t is equal to r of t integral 0 to infinity f of t dt minus you have r dot of t integral 0 to infinity, I am taking t f of t dt and so on. Now these individual integral terms I am assuming it as constants. So when you assume it as constant, let us say those constants are C0, C1, C2 and so on. Then how do you write this E of t? So E of t is, you have r of t C0 minus r dot of t C1 plus r double dot of t C2, where the C0, C1, C2 are called your generalized error constants or dynamic error constant, and the definition of those constants are C0 is equal to integral 0 to infinity f of t dt. Then when you write this in a Laplace equivalent, that C of s, C0 is equal to limit s tends to 0 f of s, which is the first error constant. Similarly C1 is integral 0 to infinity t f of t dt, that is equal to your C1 I can write in Laplace transform as limit s tends to 0, the capital T becomes here d by ds, so d by ds into f of s. So similarly you can write C2, C3 and so on. So these C0, C1, C2 up to Cn are generalized error coefficients. So first calculate these coefficients and substitute in a of t function, then you will get the error function in time domain a of t. Then to find the steady state error, you can write the equation as ESS is equal to limit t tends to infinity e of t. E of t we already calculated, that e of t you can substitute here to get the final steady state error. So this way we can find out steady state error using generalized error coefficient method. Now having understood the steady state error as well as the generalized constant method, we'll try to compare these two methods, steady state error constant and generalized error constant, to find the steady state error. So let us differentiate here. Then this I want to write here steady state error constants, steady state error constants, and here it is generalized error constants. Now, so we know that in steady state error constant Kp, Kv, Ka, the calculations are very simple. We already looked at the table. From the table directly we can find out what is the steady state error. So the calculations are simple and very easily we can find out what is the steady state error. Whereas in generalized, we already seen C0, C1, C2. We have, let us say C1, we can find out limit s tends to 0, where we need to find d by ds of the function. So those calculations are difficult in generalized error coefficient method or generalized error constant method. So what is the first point I can say here? The calculations are very easy here, but the calculations are time taking and little complex. Similarly, this steady state error constants, either it is a Kp or Kv, Ka, they can be taken as one of the design parameters as a specifications. That means, let us say my system should have, let us say peak overshoot to only restricted to 1% and settling time should be only 0.5 second. Similarly, my Kp value should be, let us say, only 2, or Ka value should be only 0.1. So in this way I can define the design specification in control system. So there we use the steady state error constant. So that is not possible. We are not going to take C0, C1, C2 as a design specifications in control system design. And third point is, which is very important, steady state error constant method is applicable for only closed loop stable systems. So you cannot apply this to closed loop unstable system, whereas generalized error constant methods can be applicable for both closed loop stable as well as the unstable system. For example, if you take a system GH of S is equal to 10 divided by S square into S plus 1 into S plus 2. This is the open loop transfer function. Now we can get the closed loop transfer function, and from that you can investigate the stability. So you will get this system is absolutely unstable system, but you can find out Ka, Kp, Ka, all error constants, and you can say your error also. But calculations wise you may get some result, but practically it is unstable system. Your system will oscillate continuously. Those oscillations are increasing as the time is tending to infinity. So that care must be taken. Whenever you try to calculate Kp, Kv, Ka or corresponding errors, the closed loop system must be stable. Whereas in this case, there is no such constraint. Straight away we can find out the error constants and we can substitute that A of t expression. Then finally we can find out the steady state error. Then what are the other things? Now, so steady state error are applicable for only standard test input signals. What are the standard? We already seen step, ramp, parabolic. These are the standard test input signals. On the combinations, that means you can have R of t as 1 plus t square by 2. So 1 is a step, t is a ramp, and t square by 2 is a parabolic. The combination we can have, but any random signal if you have, you cannot use Kp, Kv, Ka method or steady state error constant method. But in this case, anyway we are taking that R of t Taylor series expansion. Therefore, any random signal, for any random signal we can find out the steady state error. And the next is in steady state error, sometimes we may not get the accurate result, which means the accuracy of the result may not be possible all the time. In generalized error constant method, accurate result is possible all the time. And finally, in steady state error, we can say the rate of change of error is not possible. In generalized error constant method, since we have rate of change of error, because we are finding r of t, r dot of t, r double dot of t. So with that we can find out the rate of change of error. So this rate of change of error is very useful in design procedure. So when you are having a design, we not only take the error, we also take the rate of change of error. So which is readily available in generalized error constant method. So these are the pros and cons of these two different methods. But most of the design procedures, we follow the simplest method, that is your steady state error constant method or static error constant, in spite of having some of the drawbacks.